The message quickly spreads through every astronomical network in minutes. A new object is detected on observation screens in Chile. For 6 hours, observatories on 4 continents begin to adjust their schedules. This is not a protocol for a comet. By mid-month, over 200 telescopes around the world had detected a moving point, which was a complete surprise. All of this is happening in real time. The priority level rises. First to elevated, then to critical. In mid-July, unofficial rumors through flight control channels reached level 5. This designation had never been used before, neither for object ʻOumuamua in 2017, nor for Borisov in 2019, nor for anything humanity had observed from deep space. Level 5 indicates the presence of several overlapping independent anomalies. This means that natural explanations begin to crack under the weight of the data obtained. This means that all available tools are aimed at this object until it disappears forever. The European Space Agency and James Webb Space Telescopes halt their observations on August 6th. Hubble joins them. The Very Large Telescope of the European Southern Observatory in Chile also redirects its efforts. Spitzer, the newest infrared space observatory, completely changes its mission schedule. Ground stations from Palomar to Jiminy South and Apache Point utilize all available observation hours. Amateur networks with telescopes in backyards coordinate 247 hours of observations. Over 4,000 precise position measurements come from 227 observatories. This is chaotic work, crossing boundaries, budgets, and scientific rivalries. The object now has a name: Tri-Eye, divided into Atlas. 3 eyes mark it as the third confirmed interstellar guest ever discovered. Its trajectory is hyperbolic, not elliptical. He is not tied to our sun. He came from another part of the galaxy and is moving on a one-time trajectory. After he passes the sun at the end of October, he will once again rush into the void. We have only one chance. If this object were ordinary, no one would risk their schedules. Why level 5? Because a few weeks after the opening of Tri-Eye, divided into Atlas, it begins to dismantle all assumptions about how interstellar comets should look. The chemical composition does not match. The movement does not fit into familiar frameworks. The size challenges probabilities, and the trajectory raises questions that no one wants to ask out loud, but everyone quietly makes calculations. This is no longer just a scientific problem. It's an attempt to understand what we are really observing before it is too late, as the clock ticks swiftly. This is how astronomers count. They take every confirmed interstellar object ever seen and add them with critical measurements: non-gravitational acceleration, volatile chemistry, metallic signatures, orbital geometries, and early activity distances. Simple metrics, precise numbers. There is no room for guesswork. Object ʻOumuamua in 2017 had a noticeable non-gravitational acceleration. It began to accelerate, emitting gas, which became one of the most interesting anomalies. The Borisov comet in 2019 looked completely normal. A coma with high water content, characteristic carbon monoxide, and standard comet behavior in all aspects. However, Borisov showed 0 values on a small scale. It was boring. Beautiful, but boring. And now new data has emerged. I divided the results into sections. The score table filled with red in several rows. The non-gravitational acceleration turned out to be below 15 meters per day squared. This is extremely low. Comets usually move thanks to their own gas jets, but the mass divided by the area barely shifts. The reason becomes clear when you calculate the mass. To stay on trajectory while expelling gas, this object must be massive. We're talking about a core potentially 5 kilometers wide. That's a significant size. This is significantly larger than ʻOumuamua or Borisov. Discovering interstellar comets of this size in the near future is extremely unlikely. First, we had to find 100,000 small objects. The composition of the comet tells its story. Earlier observations using the James Webb Telescope showed that 95% of its composition is carbon dioxide and only 5% is water. Most comets are made of water, making this ratio paradoxical. No comet in our solar system looks like this. The presence of carbon dioxide suggests that it formed in an extremely cold region, far beyond the freezing zone of water. However, even in this case, such a ratio is unprecedented. The presence of metals opens new horizons. A very large telescope in Chile has discovered nickel pairs in the coma, which is standard for comets, except that the iron line is absent. Nickel and iron usually sublimate at similar temperatures, and form together in supernovae. Their separation requires specific chemistry. On Earth, we carry this out on an industrial scale, using processes like the purification of nickel from carbon. In nature, this is almost never found. One research group noted that such separation occurs only in artificial alloys. This is not proof of something artificial, but it is extremely unusual. Orbital geometry adds another level of complexity. I divided the data by segments. The object approaches at an angle of about 5 degrees to the plane of the ecliptic. The ecliptic is the plane in which all the major planets revolve. It is the main disk of our solar system. Interstellar objects can come from any direction in three-dimensional space. ʻOumuamua came at an angle of 33 degrees, Borisov at 44. The angles are random, as expected, but three separated objects pass almost perpendicularly to the planetary plane. It passes close to Mars in early October, near Venus in November, and glides past Jupiter's orbit in March 2026. The alignment seems convenient, statistically unusual, but not impossible. The distance of early activity also becomes an important factor. When the 1st of July saw the discovery of the comet, separated by a tail, it was already evaporating into 4/12ths and asteroids of Numisia and ʻOumuamua, located beyond Jupiter's orbit. Most comets remain dormant until they reach their destination. Or, closer, in one icy mass, sublimation does not occur at such a distance. However, carbon dioxide sublimates, and everything else contained in this core clearly evaporates prematurely. The coma was noticeable from the very beginning. 5 independent observations, 5 separate oddities. Each of them has a possible natural explanation. The massive core explains the low acceleration. The zone of extreme cold formation explains the prevalence of carbon dioxide. Exotic chemistry of nickel and carbon can explain the separation of metals. Coincidence explains the trajectory. Ice-rich and volatile substances explains early activity, but when gathered together, the probability quickly decreases. 1 anomaly piques interest. 2 are already curious. 5 together require deeper analysis. Let me clarify. We do not make bold statements, but monitor the results of the tests. Each test is simple. Does the 13th body behave like a comet or introduce new parameters? Our task today is to show you the assessment report and then explain how scientists plan to test it under pressure. After all, the essence of science lies in this. You don't need to guess. You gather data, conduct experiments, test predictions, and here is the result. It will face all the trials we can offer before it disappears forever. That is why this moment is so critical. 2 tests can quickly clarify the situation. Both are inexpensive and provide accurate results. Most people following this story have not heard of them yet. The first test is polarimetry. Light, reflecting off particles, becomes polarized. The degree and angle of polarization depend on the size, shape, and composition of the particles. You measure polarization at different angles during the comet's movement. Ordinary comets produce predictable curves. Bulky mixtures of icy dust behave one way, dense comet particles another. If the 13th body shows unusual polarization signatures, it may signal a strange structure of particles or chemistry that we have not yet modeled. It's simple here. Ground-based telescopes can conduct this test in a matter of hours. Space missions are not required. The second test is a stellar eclipse. When the 13th body passes in front of the background stars, the core blocks light for a fraction of a second. Observers around the world can detect these eclipses. Each measurement provides information about width, and by combining several such measurements, you will obtain a map of the actual shape. This method determines the sizes of asteroids even before spacecraft reach them. For the 13th body, a good eclipse defines the core radius better than any telescopic images from such a distance. Predictive maps are already spreading. Astronomy enthusiasts with 20 to 30 centimeter telescopes can contribute. This turns viewers into data collectors. These are not exotic offers, but standard tools that have yet to make headlines. Both tests reduce spores and add specific numbers that replace assessments. Both events may occur in the coming weeks. The comet is still visible. If you are interested in such deep analytical insights, stay with us. This will help to promptly update information. On October 3rd, changes will occur that will affect the geometry of observations. Mars will be in the perfect position for viewing. The comet will pass only 0.19 astronomical units from the red planet. which is about 28 million kilometers. This is close enough for spacecraft in orbit around Mars to distinguish details not accessible to Earth telescopes. The Mars Reconnaissance Orbiter is equipped with a high-quality camera designed to capture images of the Martian surface with sub-meter resolution. It will be directed at a comet, but such detailed information cannot be obtained. Nevertheless, from a distance of 28 million kilometers, he will still be able to capture the structure of the coma and possibly separate the nucleus from the surrounding gas. One quality shot could significantly refine the size estimates, which currently vary by 5 times. It could be an object 1 kilometer in size or a monster 5 kilometers long. This single number quickly disproves bold assumptions. Venus will also be in the spotlight. On November 3rd, the comet will pass 0.65 astronomical units from Venus. It's not as close as Mars, but it's still important. Observing from different angles will help recreate the three-dimensional structure. Jupiter will be the last. On March 16, 2026, after perihelion, the comet will pass 0.36 astronomical units from Jupiter. This window, where the June apparatus could potentially intercept if it has enough fuel to change trajectory. Mars will provide us the first additional angle, and this will happen in a few days. Stay with us. In 60 seconds, we will show a green object that should not glow. On September 7, 2025, during a total lunar eclipse, something strange was captured in long-exposure photos. The comet's coma shone brightly green. It is not surprising, as many comets begin to glow green when approaching the sun. This light is due to the fluorescence of diatomic carbon molecules in ultraviolet light. The C2 molecule gains energy and emits a characteristic jade glow. This is a common phenomenon for comets. However, the trio, divided into bald spots, E-double shows C-double in the spectrum. Earlier observations with a very large telescope revealed the presence of other elements that also contribute to green hues. One of the preliminary reports mentioned that this comet is among the objects with the lowest carbon chain content ever studied, making its bright green glow mysterious. 2 possible explanations remain. Firstly, perhaps the weak C-doubles finally activated as the comet approached the sun. Deeper layers might have begun to evaporate. Perhaps the C-double was hidden and started emitting gas only in September. This fits the timeline. Water vapor also began to appear later in the observation window, confirming the idea of a layered structure. Oxygen dioxide first sublimates from the outer shell, and then water and carbon chains emerge from deeper reserves. The second possibility is related to rarer emitters. Another molecule can emit a substance in a way that mimics the standard green signature. The precise lines and changes observed in September have not yet been fully analyzed. Any of these paths confirms the presence of atypical chemistry. Ordinary comets do not hide their carbon chains, and no detective work is needed to explain their color. It seems familiar, but something different is happening under the hood. The green coma looks native, while the spectrum beneath reads like a foreign language. What do you think drives this green comet? Before we reveal the leading models, let's explore the chemistry. Imagine the comet as a multi-layered freezer. Carbon dioxide is at the door, while water hides deeper. When heated, it will be the first to burst out. Other components are needed for the ordinary green dye. They may reveal themselves later, or something rare will illuminate the situation. The key point is that the standard evolution of comets assumes that everything sublimates together in predictable ratios. However, the comet, divided into Atlas, destroys this assumption. Its freezer is organized differently, and this difference tells us where it formed and how cold its birthplace was. What elements dominated its stellar cradles billions of years ago. We analyze planetary composition, and every ingredient matters. Why is level 5 important? Because it significantly redistributes resources. Telescope time on instruments like the James Webb costs millions per hour in planning and usage. This time is booked years in advance. To gain priority, a convincing justification is required. The comet, divided into Atlas, received this justification just 2 weeks after its discovery. Elite objects are not subject to easy changes. A very large telescope, Hubble, Spheric, G-Menyuk. Each of them postpones planned observations. Protocols aimed at possibilities are activated worldwide. This happens only when several independent anomalies come together. One strange data point sparks interest. 5 anomalies trigger actions. Level 5 also gives the green light for quick response mission proposals. Engineers, who usually plan 5-year timelines, begin modeling 6-month interception windows. Trajectory specialists perform calculations for existing spacecraft. Mission planners are revisiting concepts that have long awaited this moment. The proposal to redirect Juno emerged just a few weeks later. Such a turn of events is invisible in space exploration. The stakes here are scientific, not dramatic. No one is in a hurry, but curiosity drives the intense process. Every observation window matters. Every spectrum we receive is added to our database, because once the comet makes 3 orbits around the Sun and begins to accelerate away from it, it will disappear forever. No second chances, no additional missions in years. This unique event is happening in real time. Curiosity, not fear, drives everything that is happening now. Furthermore, the mystery of nickel, which the industry understands quite well. In most cases, nickel and iron act as inseparable partners. Both of these metals are formed during supernova explosions. Both are trapped in particles of cosmic dust. Both sublime at similar temperatures. When the comet heats up, we see nickel vapors in its coma. We see iron vapors nearby. This is a pattern observed in every comet that has ever been studied in detail. I analyzed the data and noticed a deviation at the end of July. Teams using spectrometers found bright lines of nickel radiation, but iron lines were either absent or extremely weak. Such separation is not observed in natural comets. Usually both metals appear together. However, in this case, one is present without the other. On Earth, the separation of nickel from iron requires complex industrial processes. The process described by humans is one example. You create nickel carbon dioxide at certain temperatures and pressures. Nickel evaporates while iron remains. This is metallurgy. It is targeted chemistry designed for purifying one metal. Houston, we have a problem. I'm not sure this is related to Florida. Fortunately, I didn't need NASA. I needed professional legal help. It turned out there was a company called Morgan & Morgan, specializing in injury cases. This is the largest law firm in America, dealing with such cases, with over 1,000 lawyers and more than 100 offices across the country. I tried to contact one of these local lawyers, but the wait dragged on longer than the delay of a spaceship launch to Mars. Meanwhile, Morgan & Morgan helped a client in Florida secure $12 million when the insurance company offered only $350,000. Morgan & Morgan only gets paid if they win the case. No upfront payments. You can file a lawsuit without getting off the couch. It's that simple. You can just click the link or scan the QR code. If you ever get injured, you can contact Morgan & Morgan. Their fee is free if they don't win the case. You can start filing a claim by clicking the link or scanning the QR code. A comet can theoretically mimic this process naturally at extremely low temperatures in a carbon monoxide-rich environment, forming nickel-carbon molecules that release gaseous nickel while iron compounds remain solid. Chemistry is similar, but very specific conditions are required for its realization. Deep cold, high concentration of carbon dioxide, and the right temperature gradient. Even under these conditions, it has never been clearly observed in comets before. Thus, a natural mystery arises before us. Nevertheless, it remains an extremely unusual phenomenon. It is a kind of anomaly that troubles researchers, not because it cannot be explained naturally, but because explaining it requires a comet formed under conditions we have never observed. Imagine sorting different sizes of coins. While